In this video, we are going to do an example where we find the outward flux of the vector field given here across the triangle with these three vertices. So let's get it started together by just drawing a picture and reminding ourselves, what does flux equal? And then I'm going to give you a chance to pause it and to try it. So let's draw a picture. So I'll draw these axes. So my y-axis, my x-axis, and then let's draw the vertices of the triangle. So it says that I have this point at 1, 0, at 0, 1, and then at -1, 0. And then I'll go ahead and connect those. I'll go ahead and connect those points. Okay, and then we also got this line at the bottom, so the whole triangle, all three sides. Okay, and remember that flux, the formula for this is I do the line integral over this curve, let me call the curve C, over that curve, because it's a closed curve. It starts and ends at the same spot. I can indicate that by drawing a little circle, through the integral. And then I do the line integral of the vector field dotted with the unit normal vector, ds. And because it's telling me it's the outward flux, if I draw the normal vector at a few points. So here, the normal vector is outwards, and it's perpendicular to the curve. It has length 1. Maybe let me draw one more at this point. I'll draw that normal vector. Okay. So we have this, and we've seen before that if my normal vector is oriented outwards on a closed curve, well, we had to be traveling counterclockwise. So I'll draw some direction arrows, counterclockwise. Because as I travel along the curve, the normal vector should be pointing to the right. Okay, and that happens if I'm going counterclockwise. Normal vector would be pointing to the right. Okay, so from here, I want to give you a chance to try it. See if you can think about, well, how do I evaluate this flux? So pause it for 5 minutes, at least 5 minutes, to try it. This is actually the most important part of the video. It's a chance for you to see the stuff that you've been watching and learning at this moment in time. How well can you use those ideas to try this problem? Like, let's see how far you can get when you're trying it. So pause it in 3, 2, 1, pause it and try it. Okay, so hopefully you did that. Hopefully you paused it and tried it. Let's talk about it. So there's two common ways I can go about finding this flux. So method one is actually do the line integral. So do the line integral. And because there's 3 different sides to the triangle, I'll have to do each one separately and then add them together. So we'd actually have to do, if we did it this way, we'd have to do 3 line integrals and then add them up. And then how do we do a line integral? Oh yeah, like involves like parametrizing the curve. We'd have to parameterize the curve so I can sub that in, and we'd have to find the normal vector for each one and then do that for each one of the pieces. But that just seems tedious because I'd have to do 3 of these. So this is tedious. I'd like to avoid it if possible. So the other way, method 2, is because we're finding flux over a closed curve, I can use Green's theorem. We can use Green's theorem. The other thing we should check is the components of the vector field, if I take any of their partial derivatives, are they continuous on my region, on the inside region, which I'm going to call R? And it turns out the partial derivatives of either of these are actually continuous everywhere. So that part's good. So when I do Green's theorem, this flux line integral becomes a double integral over that interior region R of the divergence of f. And then my notation is I write dA for the double integral. So what's the divergence of f? We've seen this a few times now. Well, you take this first component, you take this x component, and you do the partial of that with respect to x, which is 1. And you add to that, now you go to the y component, and you do the partial of that with respect to y. And that's going to be -2y. So you add those. It's 1 and then add it to -2y. That's my divergence. So I have to do a double integral over this region of this function. So I'm going to have to think about, well, what order do I do it? dy dx? Or do I do dx dy? So at this point, I want to have you do another kind of mini pause. Give yourself 2 minutes to see if you can figure out which order is going to be better. It's good review. Good review of our double integrals. Which order is better? So pause it in 3, 2, 1. Pause it and think about that. Okay, so hopefully you did that. Hopefully you tried it. So if we did dy as the inner one, I would need to draw arrows parallel to the y-axis. And it's helpful to draw at least a couple. And I notice that the function where I enter the region doesn't change. It's this bottom curve. But the function where those arrows exit the curve, well, sometimes it's on this curve. Sometimes that exiting point is on this curve. So because that exiting curve changes, if I did it like this, I would need 2 double integrals. So I probably don't want to do that. If I did dx inside and then dy, I would need to draw an arrow parallel to the x-axis. And even if I draw several of these, the curve where I enter the region never changes. The curve where I exit the region also never changes. So that will only need 1 double integral. So that's how I know I want to do dx inside. So let me space out my integrals. My function's 1 minus 2y. I know I'm going to do dx inside and then dy after that. In fact, let me give myself some more room. So now for that inner integral, I'll need these limits of integration in terms of x. Like what does x equal? What does x equal? And that's based on, if I draw, because it's dx here inside, I draw an arrow parallel to the x-axis, and I think about where does that arrow enter the region? Where does it enter? And where does it exit? Where does it exit? All right, so I'm going to need to get the equations of both of these lines. Luckily, neither of those is that bad. Both of these lines are pretty straightforward. The slope is 1, and the y-intercept is 1 for this, so that's going to be y equals x plus 1. For the other line, the slope is negative 1, so I'll get y equals negative x, and then plus 1, right? Same y-intercept. But because I have dx inside, I need these limits of integration in terms of, I need them with x isolated. So I got to isolate x in both of these. So for this entrance curve, if I isolate x, we get x equals y minus 1. For the exiting curve, if I isolate x, we'll get x equals 1 minus y. So entering at x equals y minus 1, exiting at x equals 1 minus y. For the outer limits of integration, they're in terms of y. What does y equal? And those are going to be constants based on the smallest value of y for the region, which is at the bottom, that's y equals 0, to the biggest value of y, which is at the top, that's 1. So y goes from 0 to 1. Now I'm ready to do these antiderivatives. So I get the outer integral from 0 to 1. The antiderivative of this function with respect to x, that's going to be x minus 2xy. And then I got to plug in x equals y minus 1 and x equals 1 minus y dy. Okay, now let's plug in. So I get the integral from 0 to 1. So first I got to plug in 1 minus y in anywhere I see an x. So when I do that, I'll get 1 minus y, and then minus 2 times 1 minus y times y. Okay, and then I got to subtract, big old bracket. Now I got to plug in y minus 1 in anywhere I see an x. So if I do that, I'll get y minus 1 minus 2 times y minus 1 times that other y that we have there. Whew. All right, dy. All right, so I can simplify this a bit. I get integral from 0 to 1. Let's see, this is 1 minus y, and now I can distribute this minus 2 and distribute the y into 1 minus y. So that'll give me minus 2y, and then plus 2y squared. Next up, I can distribute this negative sign to these two terms. That's going to give me minus y plus 1. With this next portion, let's see. I'll distribute the negative 2 and the y into the y and the minus 1. And then I also got to distribute this other negative in. So if I do that, I'm going to get, let's see, I'll get 2y squared with a plus, and then I'll get 2y with the minus. All right, and then I still got dy out there. So now I have a bunch of like terms that I can combine. So what are the like terms? So I got constant terms. I got the 1, I got the 1. So combining those, I'll get integral from 0 to 1. That part becomes 2. And then I have terms that have y's in them. So I got minus y, minus 2y. I got another minus y, and I got a minus 2y. So that becomes minus 6y. And then finally, we got y squared terms. I got 2y squared, and I got another 2y squared. That becomes plus 4y squared dy. Okay, so at last, it becomes a much simpler integral now. We've done a lot of the algebra. So integral from 0 to 1, or sorry, now let's do the antiderivative. So I'll get 2y minus 3y squared plus 4y cubed over 3. I got to evaluate this at 0 and at 1. If I plug in 1, I'll get 2 minus 3 plus 4/3. And then I got to subtract what I get when I plug in 0, which is 0. So 2 minus 3, that's negative 1. Negative 1 becomes negative 3 over 3. I add that to 4 over 3. Oh, that's just going to be 1/3. That is just going to be 1/3. And that's my answer. That is my answer right there. So this just reveals some of the power of Green's theorem. It can take these flux integrals over these closed curves and allow me to transform them to these double integrals over that internal region. And if this divergence ends up being simpler than what I had kind of started with, it can make doing that integral much quicker.